Swayam Prabha. Digital India. Educated India.
So like I said, we are essentially augmenting the state with a new variable. This new variable is the parameter update law. Okay, that's what we say. So your complete dynamics will look like E1 dot is E2, E2 dot is theta tilde fxt minus k2 psi 2. Let's see what else. No, did I get this wrong? Psi 2 dot will be theta tilde fxt minus k2 psi 2. Correct. So this is actually not. E1 dot is E2, this is equal to psi 2 plus psi 2 minus, okay, I don't know why that's happening, okay, and I will have theta hat dot is equal to, or in fact I will write it the other way around, theta tilde dot is equal to minus theta hat dot, and that's equal to minus gamma psi 2 fxt. Alright, and for this what was the V? So this is the entire closed loop system, okay, it's the entire closed loop system. This guy is of course the parameter update, theta hat 0 arbitrary. For the states obviously everything is given to you, right, I mean you are given the initial conditions and everything, but for the parameter update the initial condition is arbitrary. Yeah, you should start close to the true value, but you don't have to, there is no such requirement. Alright, now let us see what happens to a tracking objective. So what was the V? The V was half E1 square plus half psi 2 squared plus 1 2 gamma theta tilde squared, and V dot was minus k1 minus half E1 squared minus k2 minus half psi 2 squared. Yeah, the first one is positive definite, the second one is only negative semi definite. Okay, so obviously you have uniform stability in the sense of Lyapunov. That's one. Now we want to do signal chasing, okay, because we have negative semi definite V dot, we are exactly in the domain of Babolat's lemma, right. So we want to do signal chasing, right. So how does that look? Exactly the same steps, right. What is the first step? Yeah, I'm not going to go back. Yeah, the first set of steps is to prove that everything that shows up in V dot is going to go to 0. Oh, okay, alright, and you can even do it in a smarter way, by the way. You can in fact just, I mean some people also do this, they just try to prove that V dot is going to go to 0, because if V dot goes to 0 then each of these terms go to 0, okay, that is another way of doing it. Yeah, but I would say you stick to the steps I said, yeah, don't try to come up with your own steps. The first step in trying to prove everything in V dot goes to 0 was that you say that V is lower bounded and non-increasing, right. So I know that V is lower bounded and non-increasing. Yeah, what does this imply? implies that V infinity, which is basically limit as t goes to infinity, V of t exists and finite. This was the first step, remember. Yeah, I've done this so many years, so I know, I remember the steps. Yeah. What was the second step? You don't remember it. Okay, fine. We look at boundedness of all signals in V. Okay. So it's very obvious that V of t is less than equal to V of 0, because V is non-increasing by this, right. So if V is non-increasing, then Vt is less than equal to V0, which means that none of these can become unbounded if they started bounded, right, and they did start bounded, right. I mean, otherwise I would doubt the sanity of the simulations, okay, which implies E1 psi 2 theta tilde all are bounded signals. Now, because I am going towards Bar-Ballard's lemma, right, I want to prove that, if I want to prove that everything inside V2 is going to 0, I want to prove that these signals are LP, L infinity, and the derivatives are LP or L infinity and so on, okay. So now I want to prove that these signals are L2, but that is pretty straightforward. I am going to integrate this guy, integrate both sides, V dot t dt 0 to infinity is equal to integral 0 to infinity minus k1 minus half E1 square minus k2 minus half psi 2 square. Yeah, just integrating both sides, right. Now I know what is my left hand side. My left hand side is actually, what is my left hand side? Right, V infinity minus V0. So I am going to say V0 minus V infinity, because I am going to flip the signs on the right hand side. This is just k1 minus half integral 0 to infinity E1 square t dt plus k2 minus half integral 0 to infinity psi 2 square t dt, right. Yes. Now it should be obvious to you from just this equality that individually each of these is finite. Yes. Why? Why is individually each of these finite from this equality? I am saying this is finite, this is finite. Why? This is finite, sure. Now what? I am saying that this integral is finite and this integral is finite, just from this. How do you conclude that? First thing, is there anything negative on the right hand side? Can anything be negative quantity here on the right hand side? No, right? No, right? Because I am taking integral of a square term. So everything, the integrand itself is not negative. Therefore, if I take integral, obviously not negative. Integral is just a limit of a sum, right. Obviously not negative, not negative, plus sign, not negative, not negative, they cannot cancel each other, okay. This cannot cancel anything here, okay, which means what? If the sum is actually equal to this, individually each of them right, has to be right, otherwise, yeah, if this is bigger than V0 minus V infinity, there is a problem, this will become a greater than, yeah, but that is not the case. So individually each of them, because they do not cancel each other out, right. So obviously this individually each of them is less than equal to V0 minus V infinity, and if you notice, this is enough, right, to claim that E1 is in L2 and this gives me psi 2 is in L2, right, okay, alright. Now I can use the Bar-Ballard's lemma, right. Oh no, I am not done yet, sorry. What about E1 dot and psi 2 dot? I am claiming they are bounded. Okay, I am claiming they are bounded. What is E1 dot? E1 dot is E2. What is psi2 dot? Psi2 dot is this. I already know that psi2 is bounded. Okay, I already know theta tilde is bounded. Yeah, I just proved theta tilde is also bounded because it appears here, right. So the only requirement is that f remain bounded. Okay, so this requires me to make an assumption. Okay, notice just by the fact that E1 psi2 are bounded, x will also be bounded. Okay, it may not be obvious to you, yeah, but E1 and psi2 are basically just errors coming from the errors with the reference trajectory. The reference trajectory is typically a bounded trajectory. Yeah, you don't never give an unbounded trajectory. So you have a reference trajectory. So you are computing error between your states and your reference states, which are bounded. Okay, and if you say that your error itself is bounded, then it means you are only a bounded distance away from the reference trajectory, right? And if the reference itself is bounded, you are a bounded distance away from the reference, then x itself, the states itself also have to be bounded. Okay, so if you say that essentially error bounded means x minus here when I say states are bounded, this is basically also means x1 minus r is L infinity, right, and r is already L infinity, right. Therefore, x1 is L infinity. Okay, so basically you also have that x is itself bounded. Okay, so in order for psi2 to be bound, psi2 dot to be bounded, what do you need? You need that this quantity be bounded. Okay, not always, but when the input states are bounded. Okay, so the assumption is typically written as assume f x comma t is bounded for bounded x and all t. Okay, if you make this assumption, you will immediately have that E1 dot and E2 dot, which is minus k2 psi2 plus theta tilde fxt are bounded. Okay, and once you have this, you can use the corollary to Barbalat's lemma to claim that what? I can claim that E1 and psi2 are going to 0. Okay, I actually need no further steps, although when I showed you the application of the Barbalat's lemma, I used further steps, but right now I do not need further steps, right, because E1 and psi2 going to 0 implies what? E1 and E2 are going to 0. Okay, so I have achieved tracking. Yeah, rather amazing, although it looks like I did very simple things, some simple manipulations here and there. Again, please go back and read so you can follow. But just by introducing, so what did I do in essence? In essence, my controller, which was what we call a static controller, became a dynamic controller. What is a dynamic controller? The control depends on some value which comes from a dynamical system, right. So my control depends on theta hat, and theta hat comes from this dynamics. So just by moving from a static controller to a dynamical controller, it's almost like saying I added some integrator in my controller. Okay, not a linear integrator but a non-linear integrator. Okay, by adding a non-linear integrator in my controller, I made my system agnostic to unknown parameters. Yeah, I don't know the parameter, I actually don't know the dynamics well at all, but I exactly track the trajectory. This is not an approximation. Okay, I exactly track the desired trajectory in the absence of disturbance and all that, of course. See, all of you must have at some point or the other seen or heard of robust control. Okay, what is robust control? It's all this H infinity and this kind of control. Yeah, what is the idea in robust control? The idea is that, and that's applicable only for linear systems typically. There the idea is you design for linear systems at least, you design the control in such a way, the control gains in such a way that it can tolerate some error in parameters. Okay, but that error is rather limited. You don't know how much error. Okay, the error it can tolerate is not infinite, not significant. Okay, it can tolerate some error in the parameters. Okay, beyond that you will get only bounded performance. In fact, even with the error, you will only get bounded performance. You are only guaranteed that your system will not blow up. You are going to get a nice bound around the desired trajectory. Okay, but here what are you doing here? And I mean, I'm not saying that's a bad method or anything. I'm just saying that that's a different method. In that method, the advantage is you are not changing the control structure at all. The control structure remains the same in robust control. Okay, there is some whatever, some PD, Kx, minus Kx type of a feedback. It's like a state feedback. Okay, structure remains the same. Here it is no longer just pure state feedback. Here you have a dynamic feedback, right? You have a theta hat dot. So there is a dynamic feedback that's happening. Okay, so we have changed the structure of the control, but what have we achieved? We have achieved precise tracking. Okay, so in adaptive control you can achieve precise tracking even if you do not know the system. Okay, and that's pretty amazing if you think about it. Okay, now if I do the rest of the steps, I told you that this steps is enough. I have already achieved tracking. Okay, let's see what the rest of the steps give me. Okay, if I do the rest of the steps, I would essentially be able to prove that E1 dot and psi2 dot go to 0, right? That's what we've been doing. We started with proving that everything that is in V dot goes to 0. Then we prove that the derivatives of those quantities go to 0, and we can, yeah, we can prove that this happens. Okay, but E1 dot going to 0 just means E2 goes to 0, that we have already proved, so nothing special there. But psi2 dot going to 0 gives me what? It gives me that minus K2 psi2 plus theta tilde fxt goes to 0, right? But again, I already know that psi2 already goes to 0. So what do I have? I have that theta tilde fxt goes to 0. Okay. Unfortunately, I have not proven anything about parameter convergence. Okay. No evidence of parameter convergence, or if you folks like this, learning. I did not learn squat. Okay, I did not learn the parameter. Okay, now that's I mean, it may not seem nice to you, but that's sort of the power of this method. Yeah, it did not require you to learn the parameter. I still did pretty nice tracking control. If you give me a robot, or if you give me an airplane, or if you give me a quad rotor, I am doing my tracking. I don't care to learn some parameters. I don't care to learn the inertia. That's not my job as an engineer, right? I wanted to go to the waypoints, go to the particular formation, do whatever I wanted to do. I wanted to do the control task. I do not care if it learns the parameters. Okay, but then if you do care about the learning part, yeah, then there are some results, yeah, which are connected to what is called persistence of excitation, and these results are required also in deep learning, by the way. It may not, these don't come up obviously upfront. Yeah, you will not do good learning unless your data set is rich enough. Yeah, and how you specify rich enough, which is a very vague word, is using persistence of excitation. This idea comes from system identification. This has got nothing to do with adaptive control or learning or anything. It comes from system identification. Basically, it is like saying that eventually you are going to solve some linear system of equations, and the linear system of equations must have a solution. If it doesn't, then you can't. Okay, so that's what it comes to. You can write this E1 E2 system. So this dynamics. Okay, I guess it's done. You can write this E1 psi2 theta tilde dynamics in this linear system structure that you can see. okay, and this structure leads to some persistence excitation type results, okay. So basically you have this is what it will look like, I guess, E1 psi2 and theta tilde, this bottom right, minus k1 1 0 0 minus k2 f, and you will have 0 minus gamma f0, right. You will have something like this, I think this is correct, right, minus gamma f, right, yeah, this is absolutely right. This is the bottom right is what you will have, okay, whatever is in the bottom right is what you will have. So this is the structure that you will have, and this structure is amenable to applying some nice results on persistence of excitation, which are pretty classical, yeah, and you can actually claim that you will achieve parameter convergence also under persistence of excitation, yeah, because we do not talk about it, so I am not going to go into it in much detail. But like I said, doing further steps in Barbala's lemma is useless in this particular case, because you cannot prove parameter convergence. All you can prove is that product of theta tilde and f goes to 0, okay. Now if f is passing through 0 regularly, the function f itself is going through zeros, then this means nothing, right? Theta tilde is not going to 0, okay. But if the function f is such that it never goes to 0, is always non-zero, then yes, it means theta tilde. So you are asking something from f, okay. So if you notice, there is a nice structure here. So you see the 0 f and 0 minus gamma f, they are transpose of each other just with a gamma multiplied, right. So you are asking something on f, the last column and the last row, okay. That last column and last row has to have persistence of excitation, okay. And if it so happens that f never hits 0, then you automatically have persistence of excitation. That is a nice assumption. This is a very bad assumption. Notice, that is why I said very carefully, when I made boundedness assumption on f, I did not just make a random arbitrary boundedness on f. That would mean I am only allowing functions like sin x and all that. I am not saying that. I am saying that f is bounded if the states are bounded. So polynomial x is allowed, x squared allowed, yeah, because if, yeah, that is why I was very careful. Assume fx is t is bounded if states are bounded, if x is bounded, that is allowing polynomials. But if you just say f is bounded, then I am only allowing sinusoid and all the trigonometric functions, right, pretty sad. You see, in the space of all analytic functions, I went to just sines and cosines, right. So obviously I am significantly weakening or strengthening my requirements and weakening the set of functions that I can work with. So that is the idea, yeah. This assumption that the function does not pass through 0, even sin x does not satisfy. So I mean, you can see that it is not that easy, yeah. On the other hand, sin x is persistently exciting, so I can tell you the parameters will converge. If f of x t is sin of x, parameters will converge, okay, because it is persistently exciting, yeah, or whatever, delta persistent in this case. Alright, so that is basically adaptive control for you in a nutshell. There are of course many more cases and so on and so forth. As you can see, I have already taught an entire semester and probably do that next semester also, but yeah, so but that is essentially the nutshell of what is, yeah, adaptive control, yeah. We will do some more again new modern controls in the subsequent lectures, yeah. Alright, any questions? No? Okay, we will stop here. Thank you.